Temperature becoming more and more negative, entropy increasing in this direction. So more negative T means more entropy. Then more positive temperature means increasing entropy. So more positive temperature, hotter again. We calculated the entropy of a two-level or two-state system. It was like a random walk problem. If there are total number of n steps, or equivalently, n number of electrons with spin either up or down. So let's say there are nu number of spin ups or along the magnetic field B, and down number of spins pointing down or opposite to magnetic field. So that means if we say that this corresponds to a U energy, when the spin points up, the energy corresponding is EU, and when it points down, it's ED, okay? Or EU equal to E, and E down equal to minus E, then the energy of the system will be N up times E up plus N down times E down. I mean, nu number of particles are pointing up into their energy individually, and Nd times Ed. We did that, and this will become what? Nu E minus Nd E, and so Nu minus Nd E, right? And we call that difference equal to M. So our total energy of the system will be M times E. So we did that. How many ways out of n number of spins, Nu number can point up, and Nd points downwards. So that is given by omega equal to n factorial by Nu factorial and Nd factorial, right? And this is nothing but n factorial by n plus m by 2 factorial and n minus m by 2 factorial. That was our total number of ways we can, get Nu number of up spins and Nd number of down spins. And so this is the number of ways. So that means this is the number of microstates. Total number of microstates. Where? Corresponding to what? Corresponding to such that we have Nu up and Nu down spins. Now, which one out of the n is up and which one is down doesn't matter. For example, let's say we have only, let's say 5 spins, okay? 5 electrons, let's say 5 electrons. Now, and out of which, let's say we want 3 up and 2 down. Let's say these 5 electrons we have. So it could be either up, 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 down, down, or up, up, down, up, down, or up, down, down, up, and so on. It doesn't matter. These are microstates and more. But what is macro state is that we want 3 of them up, 2 of them down. That's our macro state. Okay? So this is the total number of ways you can do this. And we actually arrived at a formula, an approximate formula, where we took that m much, much less than n, and so we expanded this, remember, 1 plus minus m over n, and we took plus minus m over n minus m over 2n, m squared over 2n squared, an order of m over n, right? That was approximate formula. But we are going to find out the exact formula. I mean, we already knew that. And that will help us find the temperature corresponding to this system. How do we define temperature? The temperature is defined as 1 over 2 equal to del S over del E. This E is the internal energy, when number of particles and volumes are fixed. And we definitely have number of particles and volume fixed. Energy can, of course, vary because this is a canonical ensemble. So remember that we also had E equal to ME. E was individual magnitude of the energy. For a single spin. So obviously this E is constant. It could be mu dot B, but it's constant. So this is variable. So if I take a variation dE, that will be epsilon dm. And if I use it here, then I get 1 over T equal to del S by del E. So that is epsilon del M. Okay? So 1 over epsilon del S by del M. And remember, m equal to mu minus mt. Let me do it once again because I need it in a convenient form that is helpful for me. So let's take, so I'm going to of course calculate S, and that means I need, so S equal to kb ln omega, so I need ln omega. So let's calculate ln omega. So that's ln n factorial minus ln n plus m by 2 factorial minus ln minus m by 2 factorial. So I can apply Starling's approximation and write these things. So this and these are all big numbers. So we can apply n ln n minus n. And here we have minus sign. So let's take everything inside a bracket. So n plus m by 2 ln n plus m by 2 minus n plus m by 2, and then plus, because we have taken a minus outside, for this n minus m by 2 ln n minus m by 2 minus n minus m by 2. Now this n by 2 here, n by 2 here, n gets cancelled because minus minus plus. Okay, and what else gets cancelled? Minus m by 2 plus m by 2. So this gets cancelled. So all we have here is n ln n minus, let's just take the n by 2 of this thing, n by 2 ln, n plus m by 2. And then from here, again minus. So let's take this. So this will become ln n minus m by 2. So this one is done. This one is done. What remains is minus m by 2. And here we have minus plus m by 2. So let's take minus m by 2. And we have what? Ln n plus m by 2. So minus plus, again minus. So ln n minus m by 2. Right? So we have everything here. N ln n minus n over 2. Let's take just the upper part, and log 2 goes away on the other side. So let's just take ln n plus m plus ln n minus m. Okay? We'll deal with the 2 later. And here we have m by 2. So this we can just take as ln this by this, so and plus m by n minus m, right? And then here we have minus n by 2 log of half, so that becomes log of 2. So just n by 2 log of 2, and again another one from here, so 2 goes away, and log 2. Okay, so let me simplify this. I'm deriving it once again, actually, that I already did in the last class, because I want this to be in a particular form. Okay, so n ln n minus n over 2, and this is log a plus log b, which is log ab. So log of n plus n into n minus m, that is n square minus m square. Okay, and this is m over 2 ln, let's write it as I divide by n. So I get this, so 1 minus this by this, right? And then I have plus n log 2. Here though, I can write this as n by 2, and then, so I can write half and 2 here, right? And I can take 2 to the power of log. That I can always do. So ln n squared minus n by 2 ln n squared minus m squared minus m by 2 ln 1 plus m by n 1 minus m by n plus n ln 2. Now we can take n over 2 common over all, you know. And then we have ln this divided by this. So let's take a minus in front. Okay, then this will become ln this divided by this. So which becomes then ln this divided by this, which means 1 minus m squared by n squared. Okay, this is minus, so I took in the front, plus this, so this is log of this divided by this, which is this. Okay, here we have m by 2, but I have taken an n by 2 common, so 2 is fine, but an extra n I have taken, so I have to write m over n here. And this is log of 1 plus m by n, 1 minus m by n, plus simply n log 2. Oh, by the way, bracket complete. Right? Okay. Here I'm going to use a variable that will help me simplify everything. So m over n, let's say m tilde equal to m over n. If I use that, then my ln omega takes the form n over 2 minus ln 1 minus this m tilde square minus m over m, so m tilde log of 1 plus m tilde 1 minus m tilde, and simply n ln 2, right? Okay. So let me also save this variable, m tilde equal to m over n. And let me write down this one here, n over 2 minus ln 1 minus m tilde ln 1 plus m tilde by 1 minus m tilde plus n ln 2. Okay, just look at this. The m variable, what can it be? What is its range really? So m is number of spins pointing up minus number of spins pointing down. That's m, right? Okay, that's right. So I mean, either exactly equal. You have, let's say, 4 spins, 2 spins up, 2 spins down. In that case, m will be what? 0. Or your all up, if all up, then n down is 0. So basically your m becomes n up, and that is what? Equal to n, right? All of them are up, so equal to all, right? Or all of them are down, let's say. Then your m becomes what? Up becomes 0 and all down. So nd equal to minus n. So your m varies from plus n or through 0 to minus n. These are the possible values. Now if we take this on the other side, then this become plus 1, this become minus 1, and m by n is what? It is m tilde. So m tilde is either minus 1, it varies from minus 1 to plus 1 through 0. So m tilde varies from minus 1 to plus 1. So the m tilde variable goes from minus 1 to plus 1. In the middle, it's 0. We'll need that. We will need that. Okay, so this is in a useful form now. This is in a very useful form. Now, so let me write down then the entropy, Kb ln omega. So that just becomes n times Kb by 2. And this thing ln 1 minus m tilde square minus m tilde ln of, let me write that, let me spread it out. So that becomes my ln 1 plus m tilde minus ln 1 minus m tilde, right? And then of course your plus, and if you take it outside total, then that becomes 2 ln 2 just, right? Yeah. That's our entropy. Now, we're going to calculate the temperature. So the 1 over temperature, this is the absolute temperature. So it's in Kelvin, remember. It's not Celsius or Fahrenheit. It's in Kelvin. So 1 over E del S over del M. Now, if m, but we have in terms of m tilde, so let's see. M tilde equal to m over n. So, d of m tilde will become dm over n. Just that, right? In other words, dm will become just n dm tilde. Therefore, you can write this in terms of m tilde as 1 over E, and n will come out, del S by del M tilde. That's my temperature, and S is given by this. So let's see. 1 over epsilon n times your entropy's derivative. So this is constant, this comes out in front, and then we have a del m tilde of this log of 1 minus
the square minus m tilde log of 1 plus m tilde minus log of 1 minus m tilde to ln 2.
Yes. The n gets cancelled out, so this becomes kb over 2e. Let's take derivative. So minus derivative of log is 1 over log squared. And then derivative of this argument. So that becomes, this is 0 minus 2m tilde. Okay, here let's push this out. Let's write it plus m tilde. So derivative of this, first derivative of this, so is 1. So ln 1 plus m. And then derivative of this, so minus m times derivative of this is 1 over 1 plus m tilde. And derivative of this is just 1. Okay, so times 1. Then derivative of this term would be first derivative of this, so 1 times ln 1 minus m tilde plus m tilde times derivative of this. So derivative of this is 1 minus m tilde, and then derivative of this is minus 1. And log of 2 derivative is just what? 0. So let me write it down. So let me take everything here, simple minus minus plus. So kb by 2 epsilon minus minus plus, so 2m tilde over 1 minus m tilde square. I'm gone. We have this and we have this. So this minus this is this log of this divided by this. So log of 1 minus m tilde divided by 1 plus m tilde. Okay, so this and this done. Let's deal with this thing. So this is simply m tilde divided by 1 plus m tilde. Okay, we did that. Here we have plus and minus minus. So minus again, same, tilde divided by 1 minus m tilde. So that's it. Let's keep it here. Let's keep this. Let's take this on the other side. No, let's keep it here. ln 1 minus m tilde by 1 plus m tilde. Now this thing minus 1 plus m tilde into 1 minus m tilde is 1 minus m tilde square. And this time this, so m tilde minus m tilde square, and then this way plus, remember we have taken minus outside, m tilde, then plus m tilde square. This gets cancelled out, and this is 2m tilde by 1 minus m tilde square, minus. Here we have 2m tilde by 1 minus m tilde square, plus. So this whole thing, cancel this whole thing. So we have just this term. So basically kb over 2 epsilon log of 1 minus m tilde by 1 plus m tilde. That's it. That's our 1 over temperature, which will give us a temperature of 2 epsilon by kb, right? And log of 1 minus m tilde by 1 plus m tilde to the power minus 1. So I have just rewritten everything here. So the entropy is this, and the temperature is given by this. I have just written both of them here. So they're functions of this m tilde, n tilde, and m tilde varies from -1 to +1. M tilde, you remember, is just m over n, and m is nu minus nd. So m tilde equal to -1 means everything points down, n of them pointing down, and m tilde equal to 0 means equal number, whatever you know, however they are oriented, equal number of them up, equal number of them down, and m equal to +1 means everything points up, all the spins, n of them pointing up. Okay? So let's try to understand what that means. Everything pointing up means, let's say there are 4 of them, and 4 of them pointing up. What is this? It's very ordered, very organized system, right? One of them flips and you understand it's different. So this is the most ordered state, and therefore it should have minimum entropy. So you expect your entropy to be 0. There is only one way you can get all of them up. There is only one way you can get n number of them pointing up, right? I'm not asking, like, let's say 3 of them up, 1 is down, how many ways? There are some ways, but all of them up is only one way. So only one way means your omega is 1, and therefore log of omega must be 0. All pointing down is again very organized, and there is only one way you can get it. So it's once again very ordered, and therefore this too must correspond to minimum entropy, entropy equal to 0. What happens when you have equal number up and equal number down? It has the maximum possibility. So it could be this, this, or this, that way, right? So half of them pointing up, half of them pointing down is the maximum entropy state. And this corresponds to half up, half down is m tilde corresponds to 0. So we expect that the entropy for m tilde equal to +1 must be minimum, minimum. Once again, s equal to m tilde equal to -1 must also be minimum, again ordered, and s of m tilde equal to 0 must be maximum. And indeed, that's what happens. Let's try to plot this function and see how it looks. So if we plot the entropy, let's say this is -1, m tilde equal to -1, this is m tilde equal to +1, our entropy function will look something like this. It is maximum at 0, it is minimum at -1, it is minimum at +1, like this. So, just try to imagine this. So, all of your spins are along the direction of magnetic field. That's the minimum energy state. Okay, all of them pointing along the magnetic field. Now, you give it some energy to this system. You give it some energy, and some of the spins can now move to a higher energy state. That is, they can flip and become anti-parallel to the magnetic field. The more energy you give, the more they start flipping, and your energy starts increasing. And that shows you the disorder is now increasing. All were pointing up, ordered. Now some of them starts pointing down. Your disorder is increasing, but it cannot keep increasing. Why? Because at some point, all the spin ups will become all spin down. And there is no more, there is no possible way you can go on. Everything has the maximum energy and they're anti-parallel to the magnetic field. Nothing else can happen. More energy and they have nowhere to go, right? And that is the most ordered state. So again, entropy has to be zero, and that means it has to pass through a maxima, which is when half of the particles are pointing up, half of the particles are pointing down. So the entropy curve as a function of m tilde looks like this. This -1, remember, means m equal to minus n. N is the total number of spins. And +1 means m equal to n. Okay? So this is our entropy. How does the temperature look? The temperature that we have derived from the entropy is this function. Turns out the temperature looks like this. So similarly, for -1, for +1, m tilde axis, it looks like okay, so this point, you have all the spins pointing up along the magnetic field, very ordered. And this corresponds to your temperature equal to 0. M tilde equal to +1, your temperature is 0. Now, your spins were all up. Some of them start flipping down when you supply some energy. So you're giving some energy to the system and they're flipping. And look at this, what happens. It means entropy is now increasing, right? Entropy is increasing. And it looks like your temperature is going down. So it's starting from 0, but it's becoming more and more negative. Temperature is increasing in the negative direction. It's becoming more and more negative. And that corresponds to increasing energy of the system. We're supplying more energy, more flips happening, and the temperature is going in the negative direction. When the temperature reaches -infinity value, at that point, your entropy becomes maximum. Okay, your entropy becomes maximum. 50% pointing up, 50% pointing down. This part is your negative temperature space. Now on the other side, if we start from the situation where everything is, so you started with all the spins pointing down, the magnetic field pointing up, then you are at m tilde equal to -1. Now that's also most ordered state. It corresponds to entropy equal to 0, minimum. Now it's anti-parallel and the system starts, let's say, losing energy, so it's reducing in energy, and some of them start flipping up and get aligned to the magnetic field. And that means your m tilde is going from -1 towards 0. And this means there is an increase in temperature. When the temperature reaches, plus infinity, starting from 0 plus value, this is starting from 0 minus on the negative side. This is starting from the positive side of 0. When the temperature reaches plus infinity, this is minus infinity. Once again, you have totally equal number pointing up and total equal number pointing down. That's again your maximum entropy state. There is a discontinuity exactly at m tilde equal to 0. And so that's how, so you see, we have got a concept of negative temperature in situation where you have a limited bound of the energy. I mean, let us consider a single particle, right? A free particle. There is no bound, classically speaking, there is no bound how high its energy can be. Its speed can keep increasing and increasing and increasing, and its kinetic energy can go on starting from 0 to infinity. There is no upper bound. But here in this two-state problem, the maximum energy could be n times, E, and the minimum could be just n minus n times E. So there is an upper limit of energy. There is an upper limit of energy. When that happens, when there is an upper limit of energy, your entropy takes this shape. It increases to a maximum value and then drops to 0. And in that case, you always get a concept of negative temperature. But negative temperature, remember, it's not Celsius or Fahrenheit that can become minus. It is the Kelvin, the absolute temperature. So it is the absolute temperature that is becoming negative. So it's very strange. And we can go into more details of systems with spins and magnetization and all these things in details on this topic, maybe on some other day, specifically devoted to this outside the syllabus. At least this much I can comment, that when your energy is bounded above, it has a maximum value and it cannot go beyond that. If your energy cannot go beyond certain value, then you get a concept of negative temperature. And in this context, negative temperature means hotter. You supply more energy and your temperature becomes more and more negative. And therefore, if a system more negative means hotter. So look at this curve. Temperature becoming more and more negative, entropy increasing in this direction. Okay? So more negative T means more entropy, more S. If the system is in positive T state, that is on this side, then more positive temperature means increasing entropy. So more positive temperature, hotter again. More disorder. And they are separated by a discontinuity at t equal to 0. So that's all about your concept of two-state system, this entropy and its corresponding temperature. So this is the full expression for the entropy. In the last class, I derived an approximate value when your m was small. But that's not always valid, but this is always valid. Okay, so this is the end of this unit, and I would like to list a summary of this unit. But before that, let's list down some of the limitations of Boltzmann statistics. Well, one is it's only applicable to classical ideal non-relativistic gas, let's say. So far we have applied, okay? Classical ideal gas. What that means is that they do not interact. So they do not interact. They're like balls. So they are not interacting with each other. Non-interacting. To B. They're far apart. So dilute gas. How dilute? Well, if you calculate their individual Devoy wavelength, the Devoy wavelength, you know their kinetic energy, let's say, for the gas particles. From that you find out the momentum, and from that you find the wavelength of the matter wave, quantum wave associated with the probability wave associated with those particles. Your separation between two particles, average separation, if it is d, then this d must be much larger than this lambda. What that means is there are, quantum mechanically speaking, each particle, individual particle, has a wave packet associated with them, and the spread of this wave packet is about the probability wavelength, the Voy wavelength. So you have to consider that those wave packets are far enough that their distance between them is much bigger than their individual wave packet size, roughly speaking. Okay, so it must be a very dilute gas. Third, we have also seen that it must be a gas of identical particles, but distinguishable. And that's why you need the dilute concept. They're so far apart that one is here, so dilute that you can tag each one of them, although they're identical. But I know this guy is here, this guy is going this way, that guy is moving that way. You can track them, so you can distinguish them, you can name them. And that's why you need the dilute thing here. But we have seen what happens when we take these particles to be distinguishable. We're confronted with Gibbs paradox. Distinguishability of Boltzmann implies Gibbs paradox. That is, the violation of second law of thermodynamics comes out. There is another problem. If you apply Boltzmann statistics, you find that your entropy will come out to be, there will be a lot of other terms, of course, other terms here, times log of the temperature, the absolute temperature, in this form. Okay, for an ideal gas, you can derive, and we have already derived in a class. So at absolute zero, t equal to absolute zero, your entropy becomes negative. And that's absurd. That is absurd. Your minimum entropy must be the most ordered state. Most ordered state means only one macro state available. On that's the most you can go below, and that will be equal to zero. That should be your minimum of entropy, not negative. So your T approaching zero should mean your entropy approaching 0 too, and not negative. Okay, these were some of the limitations of Boltzmann statistics. Let me quickly write down a summary for you. So, one very important thing is, if you have a macrostate that corresponds to some microstates, let's say. It could be dyes that we have discussed so many times. If you have a macrostate and corresponding to that, these many n number of microstates are, let's say, allowed, then each one of them has equal probability. If probability of finding the state in this particular microstate is P, then this should be also P, this should be also P, this should be also P, this should be also P. Equally probable. Therefore, what does it mean? So this will be your total probability in that case will become P to the power n, if there are n number of microstates of finding in any one of them. So that means a macrostate that has maximum number of microstates will be more probable. So number of microstates means more probable. So probability is proportional to number of microstate. Probability of a macrostate is equal to number of microstate in that macrostate. Okay? So a macrostate that has more microstates is more probable. And because an equilibrium is a system where the system stays most of the time, that means it must have maximum probability. And therefore, it must have maximum number of microstates. So we denote it by omega. And therefore, variation of this equal to 0 gives you actually the optimum number of microstate conditions. Using that, we derived actually the distribution, Boltzmann distribution. That was n over z, gi e to the power minus beta ei, where your beta is 1 over kb2. Okay? This is the number of particles. So, this is the number of particles in the EI state. In terms of probability, if I say, I'll be saying that probability of finding a particle in the energy state EI is given by Pi equal to Gi over Z minus beta EI. That's your probability. It also means if you took a cylinder of gas in equilibrium and randomly pick a guy, the probability that it will have an energy EI is given by this. And therefore, Ni number of particles given by this expression will be found in the energy state EI. So you can use this formula to solve a lot of problems. One assignment I have given you, you will need this. Oh, the partition function Z is given by Gi e to the power minus beta EI. And we also talked about phase space. So there are two ways. Let's say you have two particles. Okay? You can completely determine the state of these two particles classically if you give me all their coordinates x1, y1, z1, their momenta px1, py1, pz1, and for the second one, so you can have this space. So if I just choose one-dimensional case, then x1 and px1. So two particles, we need 2 points there. So which will mean x, px, x1, px1, and x2, px2. Okay? Let's forget about the y and z because it's impossible to draw them. Okay? Or there is another way. We could just, have a four-dimensional space. So that's again impossible for me to draw. Let's just say, I don't know, somehow these are independent axes. So you need 4 dimension to imagine this, but just imagine that it's 4 dimension, and then you will need axes like x1, x2, px1, px2, independent perpendicular axes in 4 dimension, let's say. This space, and then only one point with the coordinate x1, px1, x2, px2 will give you the exact state. This one point in this space will give you the exact state of 2 particles. Or you can have this and give 2 coordinates, 2 points in this space. So if I extend that to n-dimensional case, n particles, then you can either draw, just a space with x and px, and you can draw n points here. Or, so this is called a mu space, let's say, both phase space. Or equivalently, you can just imagine, these are not perpendicular, but just, for the sake of the argument, imagine a space of 2n dimension, x1 axis, x2 axis, x3 axis, xn axis, px1 axis, px2 axis, pxn axis. 2n dimensional space, and you draw only 1 point. So its coordinate will be then x1, x2, x3, xn, px1, px2, pxn. And that 1 point will tell you everything about n particles. Both are equivalent. This is called a gamma space. Okay, a special kind of phase space. Now, if you go to 3 dimension, then there will be, 3xyz and px, py, pz. So this will be a 6D space. On the other hand, 6D space and n number of points. Or there will be 6n axes and only 1 point. Okay. I'll just end here with a discussion that you should study the cell. What is cell? It is the minimum size, minimum volume in a phase space. And then write down all the formulas, all the velocity distribution function, probability distribution function. What was it for pi? 2 pi m over 2 pi kbt to the power 3 by 2 v square e to the minus half m by kbt v square. That was your velocity distribution probability, and therefore any expectation value of v to the power n, you have to do dv f of v to the power n. Using this formula, if you do v, it will be v average. If you do square root and then v square, this will be v RMS. And then the most probable will be found by taking when the probability becomes maximum. So del f over del v equal to 0. Probably it will be easier if you just do del del of v square fv equal to 0. Find out that particular v square, and that's v, and that will correspond to the most probable. So let me just write down their values. The most probable, dkbt by m. The average is bt by m, and the RMS 3 kb t by m. So with this, let me just conclude this unit, and then we will move forward to the next unit, and we'll speed up